stuff kind of builds. You have to really get founded in this and be solid in it, because if you try to go on and don't understand this, it gets even worse, really bad in a little bit. I'm just telling you the facts. Now, today, what I was going to do is mention a few things about discrete convolution, which is exactly the same as continuous time, except instead of integrations, now we have summations, right? That's the only difference. And again, I'm going to put the difference. So for convolution, if you have y of t, there's a convolution of x of t convolved with h of t. We know fundamentally that's equal to the integral from minus infinity to infinity of x of tau times h of t minus tau d tau. That's the integral formation of that. We know that it doesn't matter which function goes first, so I'm not going to bother writing it a second time and reversing it. When we're talking about discrete time, we're talking about y, and there are brackets here of n. Now, I don't write brackets all the time, but if you see n, it means discrete time. N can only be integer values. Everybody follow me? Like 0, 1, 2, 3, 4. They can't be 1.31 or something like that. Y of n here is equal to x of n, the symbol is convolution like that, times h of n, and it's equal to a summation. Now the summation technically starts from minus infinity, but almost always you begin it at 0, almost always. So it would be I here would be from minus infinity technically, but we almost always just put down 0 unless there's any values that start less than 0. Then you have to turn it back, all right? Almost always it starts at 0. And it goes all the way to n here, and it's going to be x of I. It's just like this. Instead of the tau, you put an I, and it's going to be times h of, then it would be n would be like t, minus I. And it's a summation. That's the definition. So get it in your mind, the similarities. It's best you see the similarities. Then you start doing them. I'm going to show you a couple tricks too in a second. So the fundamental definition here, I said before, you can think of it just like a flip and shift, right? Remember before? I want to do one or two. I want to emphasize this too. The big difference is this. Here, the delta of n is 1 when n is 0, and it's 0 when n unequal to 0. That's the big difference for the delta function compared to the delta of t that we had before. All right, class? Now, that's it. The u of n, the next function is u of n. U of n is just equal to 1, n greater than or equal to 0. It's 0 for n less than 0. All right, so u of n is the same basic, just think of sampling the u of t. That's all you're doing at values of n equals 0, 1, 2, 4, and so forth. Another typical function you run into, but they don't have a ramp function. It's n u of n. And that's equal to n for n greater than or equal to 0, and it's equal to 0 for n less than 0. That's self-evident, n times that. Follow me? Everybody? Now, what it's good to do is, first, for me to actually go through a couple of simple examples of convolution, discrete time convolution, and then show you, if I can do this right, one or two tricks that help you. So if I say I have functions, got to tell you another thing. A lot of times they don't draw, they don't sketch the graph with little sticks, to show the height of the thing. What they'll do is this. They're going to have x, and they'll put x like this. They'll put a bracket, then they'll have some numbers, say 1, 0, 1, 0. There's only 4 values in there. And then they're going to underline where the 0 is. So if they underline this, that means n equals 0. And this would be n equal 1, 2, 3. Follow me on this, class? So they'll put an underbar where the 0 value of n equals 0 is. And that will be, instead of a drawing, they'll have this. It saves pages, you might say. Saves you a little space. So if this is my x, and I'm going to have my h to be this, 1, 1, 1, 1. And I'll put the 0 there. Make it nice and easy. Now, I think probably the best way to do this is graphically. The one with the most going on, you don't flip and shift. You all see it's that one? I got 1, 0, 1, 0. It's got a lot going on. a lot of change. Here, nothing changes, right? It's like a U of n, or sort of, right? So it's a pulse, really. So for this one, if you just graph it, remember the sum is on I here. It's not on n, it's on I, right? So now we're going to put down my x of I, and the value is 1 at 0, then it's 0 at 1, then it's 1 at 2, then it's 0 at 3. Now I take this, which is all ones, right? And I flip it, right? Normally I just have, what, like a comb, a four, I guess, element comb, and I flip it around and it looks like this. This is a simple one to see too. So this value is 1, this is 0, minus 1, minus 2, minus 3. Y'all see me on that? Now you realize at that point, for this one, n is 0, because really what we want here is h of n minus I, right? That's what we want. When n is 0, that's where it is, right? If n was minus 1, all this would shift down here. There would be no overlap. The multiplied product would be 0. You all see that? So now we start it and we just visually look at this. When I look at this, for n equals 0, I have 1 times 1 over 1. You all see that? I move it over 1, I'm going to have 1 times 1 is 1, 1 times 0 is 0. It's still 1, right? Move it over again, you can see it's going to be 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1, I have 2, right? And then I move it over again, and I get nothing on it, right? But remember, for convolution, the width will be the sum, or adding the width of the first and the second, right? So let me go ahead and, we're going to do this one. I'm going to put up what the value of the convolution is, and I'll say this right here, that y of n is going to be defined as a sum, where now it's going to be from I, it's going to start at 0 for this one, is 0, and it goes all the way to n of this function, and I'm just going to call it x of I, times this function, h of n minus I. That's what the sum looks like. I go over here, and here's what I'm going to do. Put my y of n here, and then I'm going to, I'm going to put it over here. Y of n here, and n here. So at 0, does everybody understand what I'm doing here? At 0, you all see this is going to be just 1 times 1. This is going to be 1 times 0, 1 times 0, 1 times 0. And there's zeros out here times that we'd add together, right? So it's only 1. N equals 1. Now when this moves over, and I'm going to do this on the board so you can visualize it a little better, just to make sure. This would be where n equals 1. Correct, class? Now I have 1 times 1 is still 1. 1 times 0 is 0, so it's still 1. Now when n equals 2, move it over again. We've got this, right? Again, 1 times 1 is 1, 1 times 0 is 0, and 1 times 1 is 1, so I have 2. Do you all agree with me? It's 2. When it's 3, if you take a look at this, now when it's 3, that's 2, 3. Now the whole thing is immersed in here, right? And it's 1 times 1 is 1, 1 times 0 is 0, 1 times 1 is 1, so I have 2. 1 times 0 is 0, I still have 2. Now, when it's 4, now I do this, right? Take that one down and move it out here. You all see what I'm doing here, class? Now you can see it's going to be 1 times 0 is 0, 1 times 1 is 1, and this is going to be 1 times 0 is 0, it's 1. When it's 5, you can see I have 1 times 1 is 1, 1 times 0 is 0, and the rest is just times 0, so it's 1. And finally, well, not quite finally, but just about finally, when it's 6, right? What is it?
0.
0. Correct, class? Everybody see what I did there and how I achieved it? Now, when you sketch these things, you don't have to sketch them. You can literally, I'll accept this. Just y of n. You go ahead and just go, it's 1, 1. Oh, well, won't even have to put that there. 1, 1, 2, 2, 1, 1. And if you don't even have to put the 0 down. Those are all the non-zero values. Do you all see that, class? You can add them if you want. And you can see one thing about this, it's absolutely symmetric, this particular one. That happens a lot of times. You realize, well, I better not say too much yet. But this is a simple, direct way of doing it. Now, there's another way to do it. Let me put them up here. I want to say one other thing. That quiz, both of those were homework problems. And I think we worked both of them on the board, if I'm not mistaken. So, what I'm really trying to encourage you to do is do the homework in a timely way when it's assigned before the next class period. And if you don't understand something, ask me about it. Send me an email. I'll make it a point to meet with you if you can't be at my office hours. And I'm going to be in my office every day from 11 till 12. Now, the problem I have meetings scheduled all the time. I'm going to have to miss one of these classes because I got a board of trustees meeting in Montgomery. But generally speaking, I'm in my office from 11 to 12. And a lot of times I'm there later in the afternoon as well. But I can't, because all these meetings I got, I can't make a commitment to be there between like 3 and 5 every day because everybody sticks meetings at the 3 o'clock hour on me. Just about every day of the week I got somebody throwing a meeting at me. All right, now, after that, this is one trick that I've seen. I'm going to try to do this in a simple way. If you have just finite length functions like I've shown, all right? What you can do is this, and I try to do this without causing too much problems. So you write your first function up here. Now, the last time it was 1, 0, 1, 0, right? This is going to be my x. Down here, you put h, your second function. And the second function was equal to, let's see, it was 1, 1, 1, 1. Now, make a cross-hatch grid. As such. And then you take each of these things and multiply it by the values here and fill this row. So this one is going to be 1, 0, 1, 0. As a matter of fact, they're all 1, 0, 1, 0. This isn't going to work the way I want. Well, this isn't the best example. Well, wait a second. I'm doing this wrong. And trying to explain this in the right way. If you go ahead and you look down the diagonals here, I hope I'm doing this right. I'll just show you what I'm talking about. If you talk about the values that will come out of this convolution, look down the first diagonal, and what you do is sum all the values in there. Remember, I just multiplied this times this. It's 1. Then you look down the second diagonal, sum all the values. It's 1. Third diagonal, 1, 0, 1. It's 2. Fourth diagonal, it's going to be 0, 1, 0, 1. So it's going to be 2, 5th diagonal, 1, 6th diagonal, 1, and then the rest are zeros. Now what I've done is convolution with a simple graphical trick. Let me do it again with a little more clear example, okay? Let me blow this up for you. I'm going to I'm going to just do this one, only make it a little bigger and a little easier to see. 1, 0, 1, 0. 1, 1, 1, 1. All right. All these numbers times this just repeats these numbers. So it's 1, 1, 1, 1. 0, 0, 0, 0. 1, 1, 1, 1. 0, 0, 0, 0. If you have graph paper, it's really easy to see this. I mean, some kind of big crosshatch graph paper. Now, if you do this, you have to go diagonally down here. And I hope you can see what I'm doing here. All right? Can you all see this, class? Now, along those diagonals, the way you do is you start at the top left-hand corner. That value that I sliced through is going to be the sum of all the numbers on that diagonal is the first entry, which is 1. The second entry is 1. Third entry here is 2. Do you all see this? Fourth entry is 2. Fifth entry is 1. Sixth entry is 1. Seventh entry is 0. And I might add that 0 is actually a value there. And you probably should put it in because the sum, when you do convolution, discrete convolution, the final convolved product is going to be the sum of the length of both of them minus 1. So we had 4 and 4, right? Which is 8 minus 1 is 7. And if you look here, we're going to have 7 spots. There would be a 0 here. The very end. You all see this, class? Now, both of these started at 0, correct? So you would actually put a bar under here. A good question is, what if one of them started at minus 1? Does that make sense to everybody? Then you start the whole thing at minus 1, and the 0 would be here. If one of them started at minus 1 and the other started at minus 2, it would actually start at minus 3. So you will sum together the negative values that they start at, and then shove it back that way. And likewise, if one of them started at plus 1 and the other one started at plus 2, you would add those two values together, and that's where it would start. And it's very clear if you actually do the flip and shift how that happens. Now, you can do it either way. I'm showing you this is a simple trick for short functions, right? We can keep going through the permutations. Well, what if you have, and I'm going to do this now. Suppose you have functions that exist for say all values of n greater than 0, and they're not 0, right? So these aren't pulse functions. These are something that have a long duration, like u of n. Then how do you do it? And I've got to show you this. I've got to show you one other thing, too, and this is important. Even before we get into discrete convolution, there's something that you're going to run into over and over again. And you've had this in your mathematics course. And this is where you have geometric sums. Now, I have to show you how to do these geometric sums. So what do I mean by a geometric sum? Suppose I have a summation. And I'm going to say from n equals 0 to some value, let's go to infinity. I'm going to go all the way to infinity on this one. And I'm going to have a to the n. So here, this is going to be some value a. It's going to be it could be a real or complex number, and it's in there. And but I'm going to do one thing. I'm going to qualify magnitude of a less than, actually less than 1, or else this geometric sum would grow to infinity. I want to cap it, basically. If it had a limited number of terms, then we could do it with no bounds on a, but I want to do it this way. And you've seen this. So what in fact is this? And I'm going to show you, this is the trick that you use to remember this. Well, what is that? Well, when it's 0, a to the 0 is 1. Do you all agree with that? Plus a, right? Plus a squared plus a cubed plus dot, 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 plus a to the infinity. Do you agree with me? Now, what happens if I take this sum, all right, right here, and I go ahead and I multiply it by 1 minus a times this sum? Actually, I'm going to tell you what, I am going to go to n. I'm just going to put capital N there for a reason, capital N. This will even make it easier to see. And this is going to be a to the n. Now remember, that a and this a are the same. All right, now I'm going to write them out term by term. Please just watch this. I'm going to go ahead and say, well, I know 1 times this is that. So I repeat that. I have 1 plus a squared plus a cubed plus dot, 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 plus a to the n. You all see that? If it 1 times that is just repeating the top part, right, guys? Now I'm going to go ahead and I subtract from it a times this. Well, a times 1 is a. Now just watch this. So it's minus, so it's going to be a plus a squared plus a cubed plus a to the 4th plus dot, 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 plus all the way up to a to the n plus 1. Does everybody see what I've done there? All right? You just keep watching, you'll remember this trick. This is how I remember proofs and stuff like this. I work them out and I see the beauty in the trick. Now, if you look at this carefully, what do you notice? 1 minus, there's no 1, right? 1 stays, but I got a here. Is there an a here? Yes, it struck out. Is there an a squared? Yes, it struck out. A cubed? Yes. Everything struck out, including a to the n, because there'll be an a to the n here, except for a to the n plus 1. So when you look at this, this is actually equal to 1 minus a, or excuse me, 1 minus a to the n plus 1. Does everybody agree with that? I just got rid of a whole lot of terms. I took 1 minus a, we didn't do the multiplication, I'm only left with two terms. 1 and a, 1 minus a to the n plus 1, right? But then if I divide it by this, both sides by that, now in fact I have the value of that sum without ever doing a whole lot of adding. Then I can get rid of all this and say that in fact this summation from n equals 0 to capital N of a to the n is just that. You all see this? Here's one of the beautiful things. As n goes to infinity, if a is less than 1, that term breaks off, goes away, doesn't it? If you have 1/2 to the infinity, it's 0, isn't it, class? So that means this entire sum, if n would go to infinity, would be just 1 over 1 minus a. The more fundamental way of writing this is they write this. They'll say there's summation from Q1 to Q2, these are just two values, of a to the n, it's a geometric sum, is simply equal to a to the Q1 minus a to the Q2 plus 1 over 1 minus a. And that's the value. How many remember the geometric sums from your math courses? 1, 2, 3, 4? Kind of, sort of? All right, you had geometric sums. Do you remember things like binomial expansion? Maclaurin series? Do you remember Maclaurin series? You remember all the ways of doing these expansions? What was the reason you did all these, really? The bottom line was they all allowed you to solve complicated problems with a lot less work. And same here, what I'm showing you is a trick. So you don't have to write that sum, right? And add all these numbers. It's a very clever way of doing it. So why am I doing this? Because here's a couple of things that you will get in convolution. I'm going to ask you to convolve in the discrete domain two functions. Suppose I have u of n, and I want to convolve that with a to the n and u of n. All right. Now, there's two functions. Both of them exist and have non-zero values for from 0 to infinity. Correct, class? Well, technically infinity goes to 0. So how do you do these? Now, I recommend you do the flip and shift. I just put them up there. I didn't draw them. You'll have to be able to draw them. Which one has got more going on? The a to the n u of n or the u of n? A to the n u of n. So we don't flip and shift that. We leave that guy alone. And it looks, and this is, remember, in I, this is 0, 1, 2, 3, 4, and so forth. And it looks like this. It's really, this is a to the, this is going to be a, really it's 1, and this is going to be a, this is a squared, something like this, a cubed, and you can see that this is basically looks like a decaying exponential envelope on it. Correct, class? That one you don't flip and shift. So this is my, I'll call this my x of I, and I'll call this my h, or x of n, pardon me. And this is my h of n. This is I, so this is x of I here. Now below it, I'm going to go ahead and put down my function u of n minus I. And you can see, as soon as you flip u of n, you just get a bed of nails going this way, correct, class? Just a bed of nails all the way down the line, correct? And when you look at this, the first overlap occurs when n equals 0, correct? Agreed? For n, if n's minus 1, then we start here, there's no overlap at all, correct? So it starts at 0 right here. And if you look at this, what am I really going to be doing? And I'm going to write it down now. If I say these two things, I'm going to say are the convolution is called y of n. Well, y of n will be equal to the sum from I equals, starts at 0, it goes to n, and the value is here, really, it just stops at n, right? Isn't that right, class? So I'm just got, if I stop the sum at n, I've done effectively the drawing the curtain deal, right? Now, up here though, I'm going to have a to the I, correct? Take a look at that. So that's where these infinite sums come in. I mean, this geometric sum. And if you take a look at this, well, what is this? I just put it down, right? That's going to be equal to a to the lower value, which is 0, which is 1 minus a, and then it would be to the small n plus 1 over 1 minus a. Agreed? Based on this right here. Even this, right? You all see that, class? Now that's a straightforward application of a geometric sum to a discrete time convolution problem. And you can imagine there's a variety of different things you can run into, right? I could have, for instance, this convolved with a sine of n times pi, say sine n pi, right? Or any other function. And again, I tell you, flip the one that's got the most, or I mean, don't flip the one that's got the most going on. The other one, flip and then shift it through there and write the sums carefully. It's going to take some time to, you're going to need some practice on this, so I'm going to give you a bunch of problems today. I'll give you like 3 or 4 problems to work, all right? And please make sure that you put your heart into them, try them. I'll give you the solutions, or at least the answers. Now, discrete convolution is usually a lot easier because you had at it with continuous time and you understand the flip and shift. But the thing about it is we didn't have to worry about geometric sums, all right? And that's the one thing that usually causes some people to wince. Because sometimes, well, what if you flip this one? Well, then it flipped that one, right? Then when you move it back, it's the index on a. It's a to, I mean, the exponent on a that becomes a problem. We'll do some of those next time. Is that clock right? Oh my gosh. All right, now to start in with Laplace transforms. Everybody here should have had Laplace transforms in mathematics, dude. All right, now Laplace transforms, I'll just level with you in engineering. Why I'm not worried about the beauty of the abstract transform or anything like that. What I care about is the application. The reason we like Laplace transforms is they allow us to solve the most fundamental description of systems that are differential equations. And that's why Laplace transforms are so very valuable to us for continuous time. In discrete time, you're going to see the equivalent of that is a Z transform. And that'll take a little doing to get to. But for now, we start with Laplace transforms. First I put on the fundamental, I'm going to put up the fundamental definition of a Laplace transform. So if you have any function x of t, it gives rise to something called x of s. That's the Laplace transform. S is a dummy variable. S is a value that's not observable, measurable, or anything like that. It's not in the real world. It's something used for analysis. Here, I say that x of s is the integral. Now, there's two ways to doing Laplace transforms. Some books talk about the double-sided Laplace transform. For the purposes of engineering, because we can start time anywhere we want, we start at 0. So our integral goes from 0 to infinity of x of t times e to the minus st dt. This is the definition, the fundamental definition of Laplace transform. It's very interesting if you actually look at the history of Laplace transform and the Fourier transform. Fourier came up with it first. Laplace was on his heels, added one thing to make it a little more all-inclusive. And s is a complex number. It has a real value that's labeled sigma and an imaginary value, omega. Omega here represents the frequency domain. It would be your 2 pi f. You follow me on this, class? I'll make a note of it. So, and when we talk about something called a Fourier transform, we just make sigma equals 0, and then we can do analysis in the frequency domain. Some of this I know is a bit ahead, but you've probably been exposed to this terminology in your labs and things like this. Now, S right here is in the complex plane. And when you take a look at x of s, as such, s is going to be the variable. This is the real axis, and this is the imaginary axis. And the way, there's things that happen here. When the value of this function goes to infinity, it's called a pole. So a pole would look like this. That's a pole. It just means the point in the complex plane, if you put that value in for s, you would get an infinite value for x of s. And what it really means, and you'll see this later, is the system is unstable at that point for those values. And I'll explain what that really means. There's another thing that you'll see denoted. It will be this. These are zeros. It means those values in the complex plane here, the imaginary value is 0, but suppose that's 1, all right? That value would cause x of s to be 0. So if the function was like s minus 1 and you put in s equals 1, 1 minus 1 is 0. That would be an example. All right, now, I want to tell you this. The book shows you the inverse Laplace transform. So if you're given x of s to get x of t, we never do what the book says. We never use this integral. What we do is something called, we do partial fraction expansion. Some of you remember that. And then we know the transform pairings, and I'll get to that. But right now I want to focus on Laplace transforms. And the next thing, just this fundamental definition, and we're going to use that to create a list that we will pull from, and we'll use properties to get all the rest of the Laplace transforms. Now please follow me. The first thing you're going to do, and I'll do it right here. No, I'll do it right here. I'll start with the function. My first function is going to be delta t. And this is going to be whatever the x of t is I want, this is going to be the x of s. So when I look at the fundamental definition of the Laplace transform, and I want the Laplace transform of the delta function, I go delta of t e to the minus st dt from 0 to infinity. So what does it equal? Do you remember how to do an integral with the delta function? What do you always look for? Anybody? I really hate to call on people. But if I have to wake people up, I'll call on people. Your own mind. What do you always look for if you take a delta function inside an integral and you want the value of that integral? Class. It's where the delta function does what? Turns on. And here, where would it be? 0. 0. And what does you do then? At 0 is where it turns on. You look at the value of anything next to it, right? Multiplying it, and evaluate it at the 0, where the delta. What is e to the 0? Anyone? 1. So that's the easy one. A delta function as this transform pair. All right. The next you remember this? The next transform. How many see what I'm doing here? Right? It's a straightforward thing. Do you all see it, guys? I mean, I want to make sure everybody sees it. All right. All right. It's just a straightforward thing. What if I do this? I want to know what the function delta of t minus a, or t minus a, e to the minus st dt from 0 to infinity. So I want the Fourier transform of a shifted delta function. What's that going to be? Where does it turn on? T equals what? A. What do? I evaluate what's next to it and put t equal a. So it's e to the minus sa. Y'all see that? That's e to the minus sa. And a is probably a unit of time, right? 1 second, 2 seconds. Y'all see this? All right, next function. What if I have I'm going to do this. Let's try u of t next. Well, what's the transform of that? I'm just going to I'm going to erase this and put u of t in here, right? And just watch this. Well, I put u of t in. Now, what is the value of u of t from 0 to infinity? 1. Did I need to put it in? No. Doesn't do anything. What's that integral value going to be? Well, that's technically what? Minus 1 over s e to the minus st from 0 to infinity. You all agree with that? And that happens to be what? Well, I can switch these limits, make that infinity, make that 0, get rid of that negative sign. So I have 1 over s, e to the 0 is 1 minus e to the minus infinity. Now here there's going to be some qualifications that I have to talk about later. But this is really going to be 0 for the Laplace transform. So this is just 1 over s. With me? All right, we're getting there slowly. Now, what about this function? If I have e, I could make that any number, but the book likes to use e. It could be a to the t, right? But I'm going to make e to the at u of t. And let me go ahead and make that a minus a. The reason I like to do that is now you know it's a decaying exponential. We'll assume a is strict real. Doesn't have to be, but if I take a look at this, well, what happens here? This integral I'm going to do, and I'm going to let you catch up. See, I'm up at a time break. I got about 3 minutes. I'm trying to get this in. So when you think about that, what happens? Well, when I have the integral of e to the minus at times e to the minus st dt from 0 to infinity, how do you go about solving that? Just add the exponentials, right? So now what I'm going to get is, it's the integral from 0 to infinity of e to the minus quantity a plus s t dt. And if you look at that for a second, you realize that the a plus s looks just like the s in the prior integral, doesn't it? So the only thing I can say is this: I can do it, but it just becomes 1 over s plus a. So this is 1 over s plus a. Okay? Now, we can keep populating this table. I guess the next, I'm trying to think of the most important functions to do. The properties I want to get at. That's one. I'm going to do one of the trig ones next. Suppose I had, one other thing I'm going to tell you too, for Laplace transforms, the way we do one-sided are only valid for functions that have no non-zero values below 0. They have to, all functional forms have to start at 0 for this to be applicable, these functional forms. It's very commonly used, all right? There's no reason not to be honest with you. But just wanted to state that. So the next one I'm going to do is this. It's going to be cosine of omega naught t times u of t. You have to put the u of t there so you know it starts at 0. And for this one, we do this little trick. We say, and this Euler's identity, you know cosine of omega naught t is equal to, please make sure you know Euler's, you're going to use this a lot, e to the j omega naught t plus e to the minus j omega naught t divided by 2. Do you all remember that? Now you'll notice these are two exponentials. We just dealt with the exponential, didn't we? We made the case here that this goes to this. So now when I do the I'll be done with this. I'll let you guys go. But I go ahead and I take, for the transform of the cosine u of t, I'm going to go from 0 to infinity, and I put in e to the j omega naught t plus e to the minus j omega naught t. I'll take the 1/2 out in front, and I multiply this by e to the minus st dt. This is just the fundamental definition of the Laplace transform with the cosine replaced by its Euler form. Does everybody see this? Now here's the thing that you capture. You'll see how this is really going to be 1/2 times, and it's the integral of e to the minus, and here it would be s minus j omega naught times t dt plus e to the minus quantity s plus j omega naught times t, another integral there, dt. Both of these go from 0 to infinity. Are you with me on this? And what does this really do? Well, I know these are going to fall out as 1 over, this is really what? Isn't this like, when I do this integration, I'm just going to get this in the denominator. So I'm going to get 1 over s minus j omega naught plus 1 over s plus j omega naught. And it's times 1/2. I don't have much time. Are you with me? I'm going to leave you go right. Now here's what you do. You get a common denominator, multiply this by this. It'll be s squared plus omega naught squared. And then on top, here you got s plus j omega naught, s minus j omega naught. So you're going to get 2s divided by 1/2. And it's really just s over s squared plus omega naught squared. That's where I was going. All right, that's the last thing. S over s squared plus omega naught squared. We'll do the, you'll do the sign tonight, a bunch of them. And then I'll see you this Friday. Now, I'm not going to give you a quiz this Friday. Here's why. We didn't have Monday class. All right? So what I'll probably do is give you a quiz on Monday and then a quiz on Friday the next week. That way, it'll make up for the missed quiz. But we just had one lecture with this stuff, okay? If you have questions, please see me. I'm in my office from 11 to 12 every day. So try it.
S naught plus omega naught squared. S over s squared plus omega naught squared. Right. Yeah, this is a hot mess right here. Okay. I hope the derivation is in the book because these notes are not happy.
This makes so much more sense. All the cheat sheets, like
Yeah.
that two professors gave us. I'm like, ooh, I see it now.
Have I forgotten everything from when you're differential equations? Maybe. Am I relearning everything now? Yes.
Is again? Yes. You change. I'm pretty sure.